I heard 24 through 27.
And 23.
And 23.
I already forgot.
Oh, 23 was good. I thought you took a picture of 23.
I did.
Share.
But...
Oh, it still didn't.
Oh no, y'all! I gotta make a group chat.
Yeah, y'all need a group chat with so you can send stuff. Is everybody here? Besides Kaylee. Yeah, she won't be here. Yesterday I worked this one, but apparently not good enough because now I don't work it again. I know. I'm just picking. So we're evaluating this limit. So we talked briefly in pre-cal about some identities and stuff, and I told you that we weren't going to focus too hard on the memorizing. Remember you made the little things? And I told you one was probably the most important one that we learned. Do you remember what that one was? Oh, that's a limit. I'm talking about pre-cal though. The most important identity that's used the most. Close. Sine squared. It's Pythagorean identity, so that's why it's squared. Remember a squared plus b squared. All right, so it's sine squared plus cosine squared equals 1. Okay? And you have to know that one backwards, forwards, left, right, up, down, every which way. Because you might see 1 minus cosine squared. Or 1 minus sine squared. You might have to replace some of these and use them backwards and forwards. But I say that because I see here this 1 minus cosine squared, right? Which is the same thing as sine squared. Okay? Now y'all stay with me. This is the part that everybody always gets tripped up on because it's you really have to start. Another one of what? The identity sheets? You didn't keep one for yourself?
How do you keep a graph right?
Oh my Lord. All right. So a lot of these, it's hard for me to explain my thought process on some of these on what I do because I just start trying different things. I recognize this being the Pythagorean identity just because I've seen it so much. I also know I see a sine x, I see an x. I'm thinking I probably am going to do something with that, but I don't know. I know there's nothing that I know about limits with this. I can't plug in the way it is, right? If I try substitution, I get a 0 in the bottom. That's not going to work. So I just try manipulating any way I can, doing anything that will work here to try to get it to something I can work with. So I'm going to change this to sine squared x. So now I have the limit as x goes to 0. Well, sine squared times sine is what? Sine cubed over x squared. I still can't substitute in, right? I want to get to the point where I can substitute in, but right now I'm not to that point. So I'm going to keep working with it a little bit. Now, I do know one limit. I know sine x over x goes to what? 1, right? So maybe I can get this written some way. The limit as x goes to 0. What if I did sine squared x over x squared? What does that leave me with if I pull that aside? Just sine over 1. Do you agree? Okay. Out of the top, yes. Because I was looking to make these exponents the same. Because remember that property we talked about yesterday that says I can do this and I can find this limit and then just square it, right? Y'all remember that with that exponent property? And I know the limit of sine x over x as it goes to 0. It's 1. And for sine x itself, because remember those limit properties, I can split them up. I can say this is the same thing as the limit as x goes to 0 times the limit as x goes to 0. Legal? Yes. That's that exponent property, right? And that product property that I can split them up. I can substitute here. There's no problem there. There's no undefined. There's nothing that I'm dividing by 0. And this is my old friend here that I know is 1. So now I can say, well, this is 1 squared. What's the limit as x goes to 0 of sine x? That's a simple substitution. What's the sine of 0? 0, right? Do we all remember how to do that? If I'm on the unit circle, this point is 1, 0, so the sine is 0. Do y'all need a unit circle, or do y'all still have your unit circles? You need one? Okay. And 1 squared times 0 is 0. So what's the limit as x approaches 0 of this nasty monstrosity? It's 0. And I hope you could actually, this would be a non-calculator problem, but you could graph that and see that as that goes to 0, it should be crossing at 0 or a hole at 0. Yeah. Are you asking me to go up? You want to look at it, or are you asking me to explain it? So this limit is that one I told you to highlight in your notebook. It goes to 1, right? So the limit is x goes to 0, sine x over x is 1. And that little exponent property allows me to take the exponent from here and evaluate the limit first and then do the exponent. They're fun. They're kind of like a puzzle, right? I have a jigsaw puzzle going on my table right now. I love puzzles. Disney puzzle. It's got every like classic Disney movie and like little. It's really hard school. Anyway, I just never have time to work. It's been going on there for like 3 months, and I've got like this much time. Anyway, what else? The multiple choice. So I said, can you call me? It's important. I love you, babe. No. What the heck? Okay. Like, oh well, the emergency's passed. I'm sure you got it figured out. Okay, 24. Evaluate the limit as, I love these because this was missing something I meant to tell you. It should have been log x. That really would have helped because it was just an evaluate one. Yeah. I'm going to substitute. This one you could substitute in because if you substitute 1 in, you don't get a 0 on the bottom. There's nothing keeping you from plugging anything in. So I just did the log of 1 over 3 times 1, which is, what's the log of 1? 0. Remember how that works. E to the what power gives you 1. The only way to get 1 is 0. Anytime you're doing a log and this number is 1, it's always 0. So I got 0 over, it doesn't even matter as long as it's not 0, it's not, it's 3. Because it's just going to be 0, which is A. Right, to get 1. Limit as x goes to 0, 4 times sine x cosine x minus sine x over x squared. I'm sensing another sine x over x, but I could be wrong. Let's see. First thing that I did on this one is I used that property with this constant in front, a coefficient in front, and I just kind of brought it around to the front, right? Because it said if I've got a coefficient in front, I can just bring it around. So I'm going to bring it around so that I don't even have to worry about it. I'm always looking for something that I know. I can't plug in here, right? I got 0 on the bottom. That's obvious for all of these. But I'm always looking for something that I know. And in this case, I know sine x over x is 1, right? As I go to 0. So is there any way, this was my thought process anyway, is there any way I could manipulate this so that I could get that as one of my pieces? Look up top. So Okay, that's if they're perfect squares. But yes, you're thinking right though.
Can you do like sin x over x times cosine over x? Will that help you at all?
Okay, so you're close. You're close. What I saw on this was I saw that, and I think y'all are seeing it. You just don't know where to go with it. They both have a sin x, yes. So can we take that out like a GCF? So we just factor it out, and then it'll be -1. So
Where the -1 came from. How did you do that?
I just factored a GCF out. That's all I did. Now remember, sin x over x is what I was going for here because that's one that I know. So if I separate this, and you have to remember how fraction multiplication works, right? Top times top, bottom times bottom. So if I separate this as sin x over x, I'm still left with an x here, right? Yes, but if you look back on page 21, one of those limits is cosine x minus 1 over x goes to 0. And these are, be very careful, these are all as you approach 0. Of course, as that changes, the limits change. But flip over on, I think it's page 19. That's one of those ones I told you to write down. It's 1100. Page 21, not 19, 21, I'm sorry. Those I would at least know sin x over x at a minimum. I haven't seen this one as much, but it pops up every now and then.
This one, that equals 0.
Yes. Yes. So now I have 4 times. How what? Right. So this is sin x times cosine x, right? And this is just a sin x. So all I did was I let sin x be my GCF, and I took it out so that if I distributed this back through, I'd be back up where I started. Y'all look at me like, what in the heck did I get myself into? Are y'all okay? It's just Mike. I'm just kidding. All right. So I'm going to split these up. This is obviously 1. That's the one we know. And this one, Robert said, was 0, which means the limit just goes to 0, which is D. Yes, no, maybe so? Yeah. No.
So we do need to memorize. These are just test prep.
I wouldn't memorize right now. I mean, so for you need to know the reciprocals, right? That secant is 1 over cosine. Cosecant is 1 over sine. You need to know Pythagorean identity for sure. Just the basic one, the cosine squared plus sine squared equals 1. Y'all just asked me to print this out for you. That's fine. Know that tangent is sine over cosine. Know that cotangent is cosine over sine. That's really, I mean, it's not going to hurt you to know them because they may pop up, but for right now, that's what you really need to. Yeah, no, don't go home and try to memorize all this tonight or anything like that. They give you a reference sheet, but it does not have identities on it. Actually, no, you don't get a reference sheet. If there's a reference you need, it's given to you within the problem. Like they'll say, knowing that the volume of a right cylinder is blah, find the blah or whatever it is. Yeah, so they give it to you within, but you don't have a reference sheet. All right, 26. Ooh, this one. This is typical. Yes. This is a typical multiple choice question for multiple choice. You got A. Tell me how you got A.
Well, because there's only one other thing it can possibly be. You can't get rid of A. It's either undefined or A. And I guess A.
Okay. It is the do-si-do thing. It is like squared answers, yes. It is a perfect square trinomial. Both ends are perfect squares, yes. Take the square root of the ends, multiply them together and double them, you get what's in the middle, yes? So to factor it, remember, because if a factor cancels out top and bottom, it's a whole, not an asymptote, and that does have a limit. The asymptotes are what doesn't have a limit. Okay, so if that's the case, I take the square root of the first sign, the square root of the last, squared. How do you know what's what?
How do you know it's a perfect triangle?
Remember what a perfect square trinomial means. These are perfect squares. Oh, y'all, I'm so sorry.
Whoa. What is a perfect square?
Perfect square means something multiplied by itself twice is a perfect square. 4, y'all leave Robert alone. 4, 9, 16, 25, 36. Those are perfect squares because 36, 6 times 6, right? 25 times. Right. So here, x times x, a times a. Those are perfect squares. And then the second sign is a plus. And then it's squared answers. Do you remember when we talked about squared answers? If you take the squares of both ends, the square roots of both. Yeah, we're definitely in there. Might have been an algebra 2 thing, but we use it. As long as it's a perfect square, yes. This is just conceptual because of the A's in it, right? So maybe it looks like this. That is also a perfect square trinomial. The ends are perfect squares. The second sign is plus. The middle term, square roots of the ends multiplied and doubled is what's in the middle. So to factor it, you would do x, the first sign, the square root of the last, squared. Right. So now what happens is, look.
If you factor the normal way, I did that and I got the same answer. Is that every time? Or?
Yeah, no, you'll get the same answer if you factor like normal. Like if you slashed it, you multiplied these together, yes, you can do that too. Because they were the same. Those factors canceled, which means at A, when x equals A is a whole.
Oh, because it's A, but it's A minus A, right?
And that's 0.
And then if you substitute, right? So now I'm looking at the limit as x goes to A of x minus A. So now if I sub, I get A minus A, which is 0, which is C. Huh? So 27. Yes, no, maybe so. All right, 27. I got D and E for 27, but well, are you talking to Mac or are you talking to me?
In general, like, you just go
So I just looked. Is there anything that I can do? Is there any way that I can rewrite this, do anything at all so that I can come up with a way that the whole is not there? In other words, here's what I started with, and we're just going to go, I'm going to do this so I don't have to keep rewriting it. I split the fraction up is what I did first. Plus 5, is it plus or minus? So I could essentially, for this first piece, I could get a limit, right? I'd get 0, but I still can't evaluate these, right? There's no way I'm going to be able to rework that in any way to get a 0 out of the bottom. There's just no algebraic manipulation whatsoever. So in this case, I said, well, you know what? X equals 0 must be a vertical asymptote, which means it doesn't have a limit right there that you know of yet. So D and E. Yeah. It went to an asymptote there. There's an asymptote there. There's a vertical asymptote there. Nothing cancels out. If you plug in 0, there's no way to rework this where you can get the x out of the bottom, where you can make the bottom not be 0. 13 is 14, yeah. Because so think about what this means. This is saying f of x equals 14. No matter what you plug in for x, y is going to be 14 every single time. That's a horizontal line at 14. No matter where I go on there, if x goes to -3, y is still going to be 14. You need what? More like that. All right, how are you feeling about limits so far? Not horrible. Okay. All right. Not anymore. Let's do one-sided limits first. Here we go. Yeah, I'll have to take a picture of this. One of my pre-cal classes, we talked about this. We did from one side with the little plus or minus on it. Which one? Was that y'all?
No idea what you're talking about.
If you showed me.
Okay. So we can do limits just from one side of the graph because remember how I was telling, look, if you have something like, it's easiest to show you, I think, with an example. Here's my function, right? What if I asked you, what is the limit as x approaches 1 of f of x?
-1.
It's one-sided.
It's one-sided. That's the name of the lesson.
Lesson is called.
All right, so this one does not exist, and here's why. Because as I come in from the left, it's different than if I come in from the right. Do you see that? So in order for the limit to exist, and this is a big star, in order for the limit to exist, both one-sided limits must be the same. Okay. But we can look at them separately. We can look at them as one-sided limits. And what I mean by that is we could break this up and say, well, the limit as x approaches 1, and if I do this little negative sign here, this says from the left. Remember doing it? Okay, yeah. We're going to define asymptote this way also. So for this one, if I asked you what's the limit as x approaches 1 from the left, now what would you tell me? -1. That's from the left. That's right. So then if I want to do from the right, I do a little plus sign. I felt like we did. Yes, when in behavior, we did it within behavior, and we did it from plus or minus. So if I asked you what the right hand limit was, what would you tell me? 2. The whole thing does not exist because these two are not the same. So now let me ask you this. Let me take it one step further. What is f of 1? -1.
Wait, how is it not negative? It is?
It's what?
It's the one that's filled in?
Yes. careful.
Wait. What was the last thing?
F of 1 is 1. I mean negative 1. Sorry. But in order for the overall limit to exist, in order for this limit to exist, these two have to be the same. Otherwise, you put D and E. The same value. So, not necessarily. Well, yes. If there's a discontinuity like that, as long as it's not a hole, they'll be the same coming in from both sides. But if it's a jump discontinuity like that, yes, the limit won't exist there. Let's say, I think this will answer your question. Let's look at the limit as x approaches 0 of f of x. And let's look from the left and the right. Okay, so before I do the whole limit, let's look. The limit as x approaches 0 from the left, and look at this graph. So as I come in from the left, what does that limit equal? -2. You agree? How about the limit as I approach from the right? -2. Because these two are the same thing, from the left, from the right, they equal the same thing, then I can say the limit as I approach 0 in general is -2. If they're not the same, though, then I have to say the limit does not exist. Does that make sense? Everybody okay on that? Let me give you a picture and let's see how good you are.
I have a question.
Yes?
There were never given on the homework, but it was undefined and does not exist. Would those be?
Yeah.
Okay. I wasn't sure they would be on the same question.
Yeah, no. These are just going by 1, by the way. These can be intimidating whenever you see the piecewise function itself. I want to give it to you so you see what it is we're looking at. I'll give you just a second before I start throwing things at you here.
Oh, I don't know.
Most of the time these things are graphed for us. You ready? Oh, sorry. I think I'll go ahead and do it while y'all copy. Try to make these better. graph and these equations here, tell me what you think the limit as x approaches 0 is. So let's look at it from both sides. From the right, it's 1, but what happens from the left? Nothing. In fact, it doesn't exist, right? So if they're not exactly the same, what's the limit as x approaches 0? It doesn't exist. They have to be the same. How about f of 0? I'm driving this hard because when we get to continuity, you're going to have to be able to look at all three of these things, left, right, and function definition at that point. So I want to make sure you understand. What? So coming from the right side, when x is 0.
Oh.
All right, let's look at 1. The limit as x goes to 1. Let's go from the left first. 0, right? As I come in from the left, 0. Does everybody agree? Do you see why? How about the limit as x approaches 1 from the right? 1. So the limit as x approaches 1, how about f of 1? 1, right? Look at the one that's filled in.
So that's the D and E, right?
But the overall limit there is D and E, yes. I've got one-sided limits, and because they're different, I can't have the overall limit. All right, look at 2. What's the limit as x goes to 2 from the left? 1, right? What's the limit as x goes to 2 from the right? 1 again, which tells me the limit as x goes to 2 is 1, but what is f of 2? 2. All these are the same. This is the oddball out, and that's okay. That can still happen. Why what? I'm just showing you that it doesn't have, the function value itself doesn't have to be the limit value. You can't always just plug it in to find the limit, and that's why. You know how some of them we had to manipulate because it had that hole in it. We had to get rid of that hole first, so that's why. How about the limit as x approaches 3 from the left? 2. How about from the right? Same thing, which means the whole limit is, okay, what's f of 3? In this case, all of them are the same. That's okay too. How about 4? The limit as x approaches 4 from the left? 1. How about the limit as x approaches 4 from the right? Does not exist, which tells me that the limit as I go to 4 overall does not exist. And how about f of 4? 1. Yes, no, maybe so. It's what, the best thing we've done so far? Or the easiest?
No, they have science for help science. So like we have to get help science like the first and second month.
I have a QR code.
And I
All right, let's talk about sandwich theorem then. Squeeze theorem. Then I'm gonna do a couple of the homework problems with you. It's gonna be from the book. I'm gonna run it. Because there's several things that in here that bring this all together, but I will. I will. All right. I still call this the sandwich theorem. Sometimes it's referenced as the squeeze theorem, and you'll see why. Is that how you spell squeeze?
no.
It doesn't look right.
Only one. Wait. Two.
That's how you spell it.
Okay, that does not look right.
No, I think yeah, that's right. Yeah.
Okay. Well, how do y'all write a cute day?
Yeah, that's better.
Okay. I hate this first example that they use.
So easier.
You get one from your homework. So here's what the squeeze theorem does, or the sandwich theorem. This is why I call it the sandwich theorem. We're going to take what we know about this function, okay, and we're going to say, I know, for example, most of the time there's a trig function in here, and you're going to pull the trig function out, okay? In other words, I know that sine of x always has values between what? What and what? Close. -1 and 1. Think about that sine curve, right? In fact, sine and cosine always oscillate between -1 and 1. Do we remember that? Are y'all okay there? Remember, it looks like this, the highest it ever goes. And if you think about, oh, not like that, Stacy. If you think about your unit circle, right? Cosine and sine never get above 1 or below -1, right? Are y'all following me? Okay. So here's what sandwich theorem does. It takes that knowledge that it goes between -1 and 1, and it sets up, we'll say that sine x must always stay between -1 and 1. And now we're going to take what else is hooked to the sine x. In other words, there's an x here, right? So if I come in and I give an x here, then I'm also going to do that to the two ends. So I'm going to multiply by x and multiply by x. Because that would still keep my inequality right or balanced, right? Do you agree? I just multiplied everything through by x. So now what I'm saying is that x sine x has to oscillate between -x and x. Would that make sense to you? Yeah. Yeah. Okay. So here's what I'm going to do. Because that's true, then what I'm going to do is I'm just going to come in here. I'm going to take the limit of each end. Because I don't know the limit of this, and I don't know how to find that, right? Right. Even though I guess I could just plug in 0 for that. But it said to use the sandwich theorem. So it's one of those easy examples to show you how we use it. Because initially that was my problem. The problem was, what is the limit as x approaches 0 of x sine x using the squeeze theorem? So what I did was I started with sine, sandwiched it between the values I know it oscillates between, and then I forced it to look like this. So I gave it an x, which meant I had to do the same thing to the outsides. Right? Are you with me? All right. So now here's what I have. I know, so now I just said, okay, well then if the values itself have to oscillate between negative and x, then the limits will also oscillate. I can take the limit of all of them. Right, right. Well, what's the limit as x goes to 0 of negative x? 0. This is the one that I don't know that I'm trying to find. Even though we could technically use substitution on this, we don't want to. And the limit of this side, so now it tells me that the limit as x goes to 0 of x sine x has to be between 0 and 0, which means it must be 0. That is the sandwich theorem. 9 times out of 10, you're going to take the trig function that's given. In fact, I would say probably closer to 10 out of 10 in here. You're going to take the trig function that's given to you, sandwich between -1 and 1, and then do what you need to do all the way across to find that limit. Does that make sense? Okay. It's going to be 0 or 1 for y'all right now. For y'all right now. You have to show, you'll have to, like, there'll be, every now and then, there's an FRQ with part D that says, use the squeeze theorem to show, so they're telling you what, to show that the limit of this equals 0. And that's where you're going through this. To think of it like a proof. Say again? Yes, if both ends are 1, yeah.
So why would they be different?
What do you mean?
What's the relationship there? Oh wait, it depends what the number.
It depends, yeah, yeah. For you right now, they're going to be, probably going to be all 0. Because we're going to 0 on them. Y'all okay? Sandwich them between -1 and 1 and go. All right, let me do a couple that you're going to see on your homework tonight, and then I'm going to set you loose because that's about all I have for you. I'm not getting into. Tomorrow we'll talk about infinite limits. Stop. That's exciting. No, that'll be 1.2. Yay. 3 days is a record. Not really. Assume that the limit as x approaches 4 of f of x equals 0, and the limit as x approaches 4 of g of x equals 3. What is the limit as x approaches 4 of e squared of x? Yep. It's not one-sided. This is bringing all of 1, 1 together.
Yeah, what?
This is going back. I'm just recapping some things from this whole unit. Sorry, I should. That's what I would. Remember that property with the exponents? This is testing your property knowledge. Right? I can do that. That's one of the properties. Okay, I didn't expect that one to throw y'all like that. I'm sorry.
Oh, I just guessed none. It's just 3 times 3.
That's right, 3 squared. Perfect square.
I just realized. Why does the top even exist?
Because it's defined to start with. If this is true, then find this. This is given.
Oh, I thought we were talking about three.
Oh no, I'm sorry. I'm sorry. The limit as x goes to 4 of f of x is 0. The limit as x goes to 4 of g of x is 3. That's a given. That's what I'm telling you. I'm telling you, if that's true, then find this.
Did we use the FX?
We didn't use that one this time. How about this one? What's the limit as x goes to 4 of x times f of x?
Remember what you can split off and what you can't, and how you can. Do we have to do sandwiches? No, this one's not sandwich. Anybody got it?
Yeah,
Zero, what do you do? Split it up. I'm so sorry I'm so behind on it. This one. Oh, I didn't know we were still.
I thought it was a different question.
Sorry, still saying that.
You got 4 right. No, you got. Slow your roll. Oh, wait. Oh, this is probably perfect.
That's close.
Oh, yeah, I think we have an
My bad.
they can have one. Y'all all have one, right?
How many more we need? All right, we just did number. Yeah, but it's not going to be all of them. We just did 55, part of 55. Let me tell you which ones I want you to do, and then